In our discussion of continuous random variables, we focus on two popular distributions, the normal distribution and the exponential distribution. But there are many others, and we'll briefly touch on a few of them. The first is a continuous uniform distribution. Recall the discrete uniform distribution, where the random variable could take on a realization within a range of values between a lower bound and an upper bound, and each of those realizations was equally as likely as any other to occur. For the continuous version, the PDF looks similar. It's a flat horizontal line. Remember, the value of f of y doesn't help us much. It's the area under the curve between 2 points that gives us a probability. But we can still draw some conclusions about the shape of the continuous uniform distribution. It's not skewed in one direction or another. There's no most likely value that stands out. Any interval of the same length is equally likely to occur. That is, the probability that lies between c and c plus 2 is equal to the probability that y lies between d and d plus 2, so long as both intervals lie within the lower bound and the upper bound. The PDF of the uniform distribution, f of y, is 1 divided by b minus a, where a and b are the bounds on the distribution. To find the area under the curve between points c and d, for example, we do what we always do with continuous distributions. We integrate f of y and evaluate between c and d. Recall that the cumulative distribution function, capital F of y, accumulates probability from the lower bound of the distribution up to the value y. And as with all continuous distributions, capital F of y is found by integrating f of y and evaluating from the lower bound to the value y. The lower bound for the continuous uniform distribution is naturally a, so we integrate the PDF and evaluate from a to y, leaving us with capital F of y as y minus a divided by b minus a. The expected value of y is a plus b divided by 2. And the variance is b minus a divided by the square root of 12. So when would you use a uniform distribution? First, there have to be bounds on the realization of the random variable you're describing. If there are no bounds, then a uniform distribution won't be accurate. That is, the likelihood of an interval that lies outside the bounds is 0. Also, if you collect some data and you see the histogram generated for those data shows the classes of the histogram are roughly equally likely to occur across the bounds of the variable. Suppose the amount of time it takes to assemble a frozen banana at Bluth's original frozen banana ranges from 27 to 39 seconds, and that the assembly times are uniformly distributed. Let's find the probability that a given assembly will take between 30 and 35 seconds. We could integrate the PDF and evaluate between 30 and 35 seconds, or we could evaluate capital F of 35 minus capital F of 30. That's 35 minus 27, all over 39 minus 27, which is 0.667, less 30 minus 27, all over 39 minus 27, which is 0.25. The probability that a given banana will take between 30 and 35 seconds to assemble is 0.417. That is, around 42% of bananas take between 30 and 35 seconds to assemble. 0.417 would be the same probability for all intervals of the assembly time random variable that are 5 seconds wide. Another continuous probability distribution is the Weibull distribution, named after its originator, Wolodi Weibull, a Swedish engineer who unfortunately had no particularly interesting facial hair. The Weibull distribution is very common in reliability engineering, particularly in analyzing the time between failures. It also has uses in survival analysis, or an area of biostatistics that studies the time between medical events. Many of the applications of the Weibull distribution model a random variable that's describing the time between events. In fact, a special case of the Weibull distribution is the exponential distribution, though we generally don't use the term rate to describe one of the Weibull parameters, of which there are two. We represent these two parameters as alpha, the shape parameter, and beta, the scale parameter. When alpha is 1, the Weibull becomes an exponential distribution. Note that the Weibull distribution is truncated at 0, which makes it a good distribution for time, as we can't have negative amounts of time. The gamma distribution is another continuous probability distribution that also has application in failure times, but also has been used to describe the occurrence of rainfall amounts and in modeling the likelihood of different losses for insurance purposes. The gamma distribution is a general form of several distributions that are special cases of the gamma, including the exponential distribution and the chi-square distribution, which we'll talk about in a later unit. The gamma distribution also has two parameters, which I refer to here as alpha, the shape parameter, and beta the scale parameter. The gamma distribution also contains what is called a gamma function, which makes calculation a little more difficult for non-integer values of alpha. The gamma distribution is also truncated at 0, therefore a random variable modeled with a gamma distribution can't take on negative values. One last distribution I'd like to mention is the triangular distribution. Both the uniform and triangular distributions are useful in cases where we have to elicit bounds from experts. That is, maybe we don't have data describing a phenomenon, so we can't determine what probability distribution would be a good fit. Instead, we have to rely on someone telling us that the range of values that the random variable could take on is between some lower bound A and some upper bound B. With the uniform distribution, that's all we get. With the triangular distribution, we get one more piece of information. That is value C somewhere in between A and B that's most likely to occur. What's another term for the most likely value? The mode. Parameter C here represents the estimated mode. This makes both the uniform and triangular distributions good for assessing a subjective probability, that view of probability where we couldn't describe the numerator and denominator in a probability calculation exactly. That is the classical probability view. Nor could we view past history to find the number of ways that a phenomenon occurred, that is the relative frequency view. Here we may mix some past history with some subjectivity to describe the minimum, maximum, and most likely values. It has a piecewise PDF describing the distribution between A and C and then between C and B. And there you have it, an introduction to a few other distributions that you might encounter. If you'd like to read up more, Wikipedia has good descriptions of each, and many different stats textbooks will give varying amounts of information about each, along with some examples. And of course, there are many more probability distributions. These just represent a few.